room here. The slides that you have that I posted will mostly follow this. There are a couple of exceptions. I threw in, a couple of clicker problems. I also threw in one slide that just goes way back to I think lecture number 1 or 2, something like that. So it's just a table that we're looking at for reference. Okay, so that should be the only difference with the slides you have versus what I'm going to show today and Tuesday. We will eventually get to talking about common dimensionless groups. So these are specific numbers that are used, dimensionless numbers that are used, or comparisons that are commonly used in fluid mechanics. We won't get to too many of those in this class, but if you were to take an advanced class, you'd spend more time thinking about those on a little bit. We'll do one little example of correlation to experimental data. And I'll explain why that's important through today's lecture. On the right-hand side, one of the things that is quite common, this is a model, meaning a true physical scaled down model of some apparatus, the end of a boat, I don't know, a submarine, something like that has been put into a wind tunnel to study how fluid mechanics act on it. And so that's quite common. That is going to motivate us for why we're doing dimensional analysis. That essentially we don't want to build a huge public works for some reason and have it not work. And so we've figured out ways to scale things down appropriately. And the key part here is appropriately, so that we can measure certain quantities, relate them to each other, and have some predictive power on how the real system will work if it's built as designed and in proportion to what we have made at a small scale. Okay, so announcements. Don't forget the new extra credit opportunity. By the way, I'm about halfway through grading the first round of extra credit that a lot of you submitted. So I'll try to get those done certainly over the weekend, but I'll try to get them done tonight so that you just have some sense. So if you don't see any grade yet, it's because I haven't gotten to it. And I did start at the top of the alphabet. So sorry, everybody down at the bottom of the alphabet, but I will get to you soon. And let me see. Oh, another thing, that new extra credit opportunity, by the way, now is out of 0 points, meaning that if you didn't submit it, there's no penalty, right? We're not trying to add up points that don't exist. And so it's out of 0. The most you can get is 10. Let me know if you have any questions on it. The final will be Sunday, a week from this coming Sunday, May 2nd, from 4:30 to 7 p.m. There were a number of questions last class about getting prepared for the exam. So what I would like to do is have next Thursday's lecture be dedicated to kind of an overview of what we've talked about, with some emphasis perhaps. I will lay out for you at that time the actual sort of proportion of questions and so forth. What I can tell you right now is there will be 4 long answer questions. One of them will be focused on material from midterm 1 from midterm 2, and then 2 of them from basically the most recent work, which is linear momentum to current, to what we're talking about now. So that's just the long answer, or long questions, long calculations. I wrote down sort of a breakdown. I haven't refound it yet for how the other 2 parts, but we will have the same style. It'll just be a bit longer, same style of exam, just a bit longer. So if everybody turns in their homework on Thursday, at midnight on Thursday night, we will release the solutions for, I think it's only homeworks 10, 11, and 12. I'll go back and check, but I think it's only 10, 11, and 12 that we have turned in since the last exam. And you'll have those solutions to work from in studying for the exam. And then I will also put together another sort of set of practice questions. Those will not be in the form of an exam necessarily. They will only emphasize the last third of the material that we've covered, i.e. from linear momentum to current. That is, you've already got material from the first 2 exams. Go back over that. Don't forget about that, because this is a cumulative exam. All right. Any questions before we dive into working on problems here?
So normally when you post the practice questions, there's not a solution. Will there be a chance for office hours after you post the questions for us to talk about it?
Sure. Yeah, we could do that. Let me think. I could easily do that on Friday, which is after the last day of classes, right? So our window is kind of compressed here, right? Between Thursday and Sunday, right? When the exam is. So I'm happy to do that either Friday or Saturday and maybe just set aside 2 hours. I guess I'd just like some feedback as to which is going to be more useful to you based on whatever else you have going on. Like, is Friday too early because you won't have worked on anything yet? Is Saturday too late because it's too close to the exam? I'm happy to do it either way. Just not during an Avalanche game. I have to watch the Avalanche, so.
Either is fine for me, but
okay. I tell you what, go ahead. If you have a strong opinion about Friday or Saturday, pop it into the chat, and hopefully Alexi or Emma could just, if you could just kind of take a tally of kind of what the sentiment is, I'll plan for that. And then I'll let you know Monday or Tuesday what the plan will be, whether it's on Friday or Saturday, and we'll have those 2 hours. So, yep, happy to do that. Great idea.
Just a couple quick questions for you, Professor. One is, will it be the same format where you'll be on the Zoom room and we can pop in with questions like we do for our exams?
Yep.
Okay, awesome. And then my second question is, for the first 2 midterms, will there be solutions posted for those?
I don't have solutions written up. The way I do the solutions is I work on them in a spreadsheet. And so what we've tried to, like a Google Sheet, what we've tried to do is give you, well, I think we've tried to give you the guidance in the comments how to do those problems correctly. But we're happy to answer those questions as part of the, like if you have specific questions, certainly email us. If you want to talk about those in office hours, that's totally fine. But our goal, I think, in trying to give you feedback on those problems was hopefully to kind of steer you back on the right track. If that's not enough, then certainly engage us.
Okay, awesome. Thank you.
You bet. Anyone else?
I guess I just want to say in people in the chat, almost everyone voted for Friday. There's about 15 people, so
okay.
Up to 15 people, yeah.
We'll right now we'll tentatively. I need to look at my schedule and figure out Friday, but I don't know that I have a whole bunch scheduled, but I do have a few things I know I have to work around. Just, if you've got strong opinions about Saturday, throw them in, and I'll check in with Alexi at the end of class to just see where that lands, in case there's 16 people that now jump in on Saturday. So no worries. Okay. All right. If there's nothing else, I'll go ahead and get started. Okay. Oh, come on. Rats. Somehow. Oh, I know what happened. Okay, there we go. All right. So this last problem that we didn't get to on Tuesday was essentially looking at energy losses again, where we have kind of 2 different scenarios. So we have these 2 reservoirs. They are 50 feet different in elevation from each other. And we're told that in case number 1, water flows by gravity from one lake to another. So obviously that's going to be from left to right, the higher one to the lower one. And at a steady rate of 80 gallons per minute. What is the loss in available energy associated with this flow? Okay. So we've got that loss. All right. We're going to have to calculate that. So that's kind of part 1 of this. Part 2 of this. Okay. Now, so let's say you have the same loss that you calculated in the first part. Now, what if we go ahead and pump the water back up from the lower reservoir to the upper reservoir? If we do that and we have to account for that loss that's occurring, along with the energy change between the two, how much pumping power do we need? Okay, so the first part, so this is kind of a clever way of just getting us to identify or populate all the pieces of the full energy equation, which we'll write out in a moment. The first thing that we're going to do, let's just take a step and convert Q, the flow rate, into something a little more meaningful. Now we're given 50 feet is the elevation difference. So let's go ahead and convert 80 gallons per minute to cubic feet per second. We'll just have that set aside. And then we'll work through the first part of this problem on the next slide. And the slide after that, we'll work on the second part of the problem. All right. So I guess I have to get my pen going. Working a different color today. Q is equal to, by the way, I think I solved, it's only the 14th week of class, and I think I solved my problem with the tablet not always reading my pen. I'm hopeful. Let's see if I may have doomed myself by saying that, but let's see what we can do here. All right, so we have 80 gallons per minute. And of course, we need to convert to cubic feet and seconds, right? So we're going to multiply by 1 minute. Oops, limb. 1 minute. Goodness sakes. 1 minute. That'll be a really thick one. Gives a per 60 seconds, right? And then we also multiply by 1 cubic foot, 1 cubic foot is 7.48 gallons. All right. Okay, so when we work this out, Q comes out to be 80 gallons per minute. Turns out to be 0.178 cubic feet per second. Okay. So that's a little more useful to us. So for part A, or part 1 of this, A is going to be, let's figure out the loss when we're draining. Then in part B, we're going to take that loss and sort of add to it and say, okay, for part B, we're going to have the loss from A and have to figure out the energy needed to pump that water back up 50 feet to get back up to reservoir A, okay? Now, if you were working through the real world system here, you would care probably about what is the diameter of my pipe, what is it made of? In other words, like wrought iron would be different than cast iron, would be different than concrete, etc. You might also care about the total length. We're kind of idealizing this at this point, okay? We are coming up with some losses. We will do that in part 1 here, but more importantly, I just wanted you to note that we could get far more specific about the losses and so forth if we had more detail. So, okay, so in our simplified world here, we're going to work with, let's do part A first here. That's the reasonable sequence. So part A, let's go ahead and write out the full energy equation, and then we can think about how we simplify it, right? Remember, because we're calculating the energy losses, it makes sense that our first step is going to be, how do I inform the entire energy equation, where location number 1 is going to be this lower elevation reservoir here at the surface, and location number 2 is going to be the surface of the upper reservoir. All right. So we've got our notes tell us we have P out over rho plus V out squared. And I realize I'm using out. I will convert to 1 and 2 when we take the next step. V out squared over 2. We've got plus G times Z out is equal to P in over rho plus V in squared over 2 plus GZ in plus some lowercase w shaft in and minus any losses, right? So I didn't get that one in on the far end, but if that was all in one line, the loss would be on the same line there. Okay, so what gets simplified? For part A, note that there's no mention of turbines or pumps or whatever. Part A, remember, is just we have flow going that direction. Okay, well, if that's the case, this piece here goes to 0, right? We know that the pressure at point 1, which is on the inside, the inside of this system, is 0, right? It's 0 gauge. The out pressure is also 0 because that's at the surface. We also expect that the velocities at both location 1 and 2 are equal to 0, right? So that's 0, this is 0. And what are we left with? Well, something pretty straightforward. The change in elevation here, so Z out minus Z in times G is equal to a negative loss. Let me rearrange that and write it here. So now we have the loss is equal to, and I'm just going to distribute this negative term when we move the in to the other side. So this is going to be equal to G times Z in minus Z out. Or we could rewrite that as G times Z1 minus Z2. Okay, so I think, yeah, that should work. All right. So now we can inform this, right? So we can write, we know what G is, 32.2 feet per second squared. And then we multiply by the 50-foot difference here. So Z1 minus Z2 is essentially 50 feet. Oops. No, I see. I think I'll bet the comments coming through. Let's see. Did I goof this up? So out minus in. And then when we switch that up, we go in minus out. Why did that come out to be a negative? I feel like I goofed something up here. Because, well, no, let's see. G times out minus in. And then when I multiply through by a negative, it becomes in minus out. In is 0, out is 50. And that ended up being a minus 50. That doesn't seem quite right. Where did my math go wrong here? In minus loss. No. Just skip the step. So let's see. Loss minus loss is equal to G Z out minus Z in. Right? And if I go through and multiply through by a minus, I get loss is equal to a plus in minus out, and that makes a minus 50.
Isn't Z in Z2 since we're going down?
Thank you. I had it reversed. Thank you, Natalie. You're absolutely right. The way I right. For part A, I even drew the arrow. You're right. Thank you. Okay, so that means that this is the part that's wrong, right? So if I translate these to 1 and 2, because in is from the left reservoir, out is the right reservoir. Yep, you're absolutely right. That is the way that goes. Okay, so that looks terrible. So let me rewrite this. G times Z2 minus Z1. Right? Yep. Okay, and this just looks terrible. I was just trying to rewrite it to make it a little clearer, but didn't come out that much clearer. Okay, so now we're just multiplying by 50 feet. G times Z2 essentially because Z1 is 0. And then we could multiply by a conversion factor. So this would come out to be 1,610 foot squared per second squared. But we can convert this to basically 1 pound divided by a slug is equal to a slug foot squared per second. I thought I had this worked out, but boy, it doesn't feel like it now. This would just come out to be 1610 foot-pounds per slug. Now remember that this version of the energy equation is energy per unit mass. So it's good that we have slugs in the denominator, right? The energy component of this is foot-pounds or pounds times feet, however we want to look at that. Foot-pounds is kind of the common way to say it. Okay, so there is the energy of our loss in terms of per mass. All right, so that's part A. Now in part B, we want to reuse this equation with the information that says that now my minus loss is minus 1610, okay, for working this out. All right, are we okay to go to the next slide? All right, next slide then. For part B, now I can get this worked out. Let me change colors. I'll go back to red. So for part B, we're going up this way, and we have loss plus pumping, and this is now 1, and this is now 2, okay? Which now finally lines up with my conceptual model that I had incorrect before. All right, so P, I'm going to change these instead of out. Let's just convert these to 1s and 2s. P2 over rho plus V2 squared over 2 plus G times Z2 is equal to P1 over rho plus V1 squared over 2 plus GZ2, Z1, GZ1 plus this work, shaft work, that's a lowercase w, and we're calling that a net inflow if it's positive, and then minus our loss, right? Where our lost energy now we calculated in part A. So we have the same things happen, right? We know that pressure 2 is 0, pressure 1 is 0, the velocity at 2 at the surface of the reservoir is 0, the velocity at the surface of the first reservoir is 0, and so we have a slightly different term now. And what I'm going to do is just rearrange it to solve for little w is equal to, shaft in, I guess, is equal to, so now we're going to put the loss on the other side. So we end up with loss minus G Z1 plus G times Z2, right? So that was just the algebra to get that far. Now I can clearly group these a little bit. The other thing to note is that, so I guess why don't I just go ahead and just say this is loss time, plus G times Z2 minus Z1, right? And in this case, again, we will end up with 50 feet in that. So we know what this is, we know what G is, obviously, we've calculated our loss. However, if we want this to be in the pumping power required, remember power, when we're talking about that, now that's our capital W with a dot on it. So it's an energy flow rate. So this W dot shaft in is equal to M dot times little w shaft in. Okay, so this is now M dot, of course, we know is rho times Q. So we've got rho times Q times now this loss plus G times Z2 minus Z1. Okay, and now we can inform this. We know what these numbers are. Right, we're given that Q is equal to, well, we had figured it out on the previous slide, right? This was, back here, 1.78 feet cubed per second. So let's go back here. So we've got Q. We know that rho is 1.94. We've calculated the loss. We have G, and we know Z2 minus Z1. Let me think. Nope, I think that should work out. Okay. Okay, so let's go ahead and multiply this out. So we end up with 1.94 slugs per foot cubed. Well, I really thought I had this fixed. This is amazing. This is worse. I basically traded out my dongle thinking that was the big part of the problem. Times, and then Q is 0.178. That's supposed to be a 7. 8 feet cubed per second. Come on. And then we multiplied by our loss, which was 1610 foot-pounds per slug. And then we, oh, sorry, I got that in the wrong spot. Then we add this other quantity here. So we've got 32.2 feet per second squared times, in this case now, just 50 feet minus 0 feet, but we'll just leave it at 50. Close the bracket on that. And essentially we could have gone through the same translation that we did for units. So this 32.2 times 50 will end up being feet squared per second squared. We can convert that to foot-pounds per slug. They're equivalent. And so what we end up with then is W dot shaft, this pumping power, come on, is equal to 1110 foot-pounds per second. And if we were to convert to horsepower, that would end up being 2.02 horsepower. So not a terrible lot of power to basically overcome that loss and get the water back up 50 feet of elevation from reservoir, the lower reservoir to the upper reservoir. I guess I'm trying to be careful not to use the numbers because we switched them, the 1 and 2, based on the direction of flow in that case. Okay. Any questions on that? Okay. So for now, let's kind of put the energy equation behind us. Obviously, we'll bring it back for the exam next week. But for now, let's switch gears and talk a little bit about this notion of dimensional analysis. And this is a fairly critical skill that a lot of people use for trying to do things that are basically, we can think of them as being somewhat unprecedented. All right. So, for example, here is a scale model on the upper left-hand side of the Three Gorges Dam. On the bottom is sort of a foggy picture of the dam itself after it was built. And on the right-hand side, you see 2 aerial images, one from April 17th, 1987. This is before the dam was put in place. The dam was put in kind of down here. Now you can see it in place. And by November 2006, you now see the reservoir sort of backing up the Yellow River here. Okay. So pretty impressive, obviously. But before you make an enormous investment like this largest dam in the world, you want to try to study it as best possible in the most feasible way to be able to predict how it's going to function. Another view of this is some models of New York City down around the neighborhood of the in Manhattan and the World Trade Center. And on the left-hand side, you can see the World Trade Center, the sort of the tower there, sort of illuminated on the left. And this is sort of doing the scale modeling of what was the dispersion of the materials that came out after the planes crashed into the World Trade Center, trying to figure out how big that plume would be, for example, right? Knowing you've got water on, kind of two sides of this end of the island of Manhattan, how does that disperse and where does it go? Where do you look for challenges downwind, so to speak? All right. So we can use these models. They're a lot cheaper than sort of making mistakes at full scale and having to go back and reinvent things. So the problem is, if we are interested in studying how pressure drops across a smooth-walled water distribution pipe, for example, there are currently no closed-form mathematical relationships that will accurately predict the pressure drop. And in the lab, we could try to develop some relationships to predict how pressure drop is somehow related to the other factors that are occurring there, maybe the diameter, right? The context of a particular setting. So what are the important variables for the problem? If we wanted to create a laboratory scale model, what are the things that we would measure and relate to each other in some way so that we could come up with some predictive relationships, all right? So that's essentially where this is going. So what are the important variables for this problem? All right, on the next slide, let's answer that. So we're looking for some pressure drop. I'm just going to give it delta P sub L with length, right, as we go from one position to another. And we expect that to be some function of what kind of factors? Maybe the diameter of the pipe, right? So D might come into play. Maybe also the density of the fluid, right? How dense is it? That has something to do with sort of inertia, right? Being able to move it. Also, another thing that we've talked about, not in great detail, but we did back in week 1 or 2 of the class, is its resistance to movement, right? The viscosity. So something like mu, the dynamic viscosity. And then, another property of flow that probably is going to matter is how fast are we going at any one time? How much energy, kinetic energy, is included at any one moment? So we might care about the velocity here, all right? So what I've just written is something that we could have argued to some extent about what matters. You might have said area, and I would say, well, area is important, but ultimately that's controlled by diameter, right? Like we could boil this down to D, the diameter. You might also say, well, what about flow rate? And I'd say, well, D matters for the area, kind of cross-sectional area, but D and what are related to Q? Well, D and V, right? D controlling area and V the velocity, right? Those two, we're trying to boil things down to more fundamental parameters than just saying flow rate, for example, or area. Those are a little bit of, they're kind of one step removed from something more fundamental, which is diameter, which controls area, and velocity, which has some control over flow rate, right? And the reason for this is that I'm just going to give this away when we'll talk about it in a second, but this is dimensional analysis. Remember, our dimensions are FLT, force length time, or they are MLT, right? Mass length time. Those are dimensions. We convert those into units depending on whether we want to work in the Scientific International or whether we want to work in imperial, right? So those dimensions are translated into units at some point and have some, real measurement to them. But for now, we're just going to focus on the dimensional part of this. All right, so if we tried to analyze all of the possible combinations of how these variables affect, basically these variables affect the thing we care about, predicting delta P sub L, right, our change in pressure with length. it would require at least 16 time-consuming and expensive experiments, because we want to look at how does rho change with D, how does rho change with mu, how does rho change with V, right? All of those things. And then we would do the same thing with V. How does V change with mu? How does V change with D? All of those things would come together, and ultimately we're trying to get them to feed back to this some predictive model, numerical model, meaning a curve of some kind, some relationship that we can use to predict the change in pressure with length based on these variables included. Okay. Oh, so we avoid this having to develop 16 complicated and expensive models by not working with the whole list of variables. And instead, what we do is we collect the variables into a reduced set of non-dimensional variables. So that should be an A, variables. Using something we call the Buckingham pi theorem. Okay, and we'll talk about the details of that in a moment. Many fluid mechanics applications are just too complex to use the relationships that you've seen so far. And so we have to come up with other ones. In these cases, we use experimental data describing the system must be used to establish how results found in the laboratory will relate to a real system, okay? So this is not as simple as saying, well, if I want to build a dam 50 feet, tall and 100 feet wide, I just need to divide all the dimensions by 10 or even smaller, by 100, and I can build it in my lab, and then I can run some experiments on it and expect everything to appropriately scale. Like, for example, if you got a velocity out of spilling water over that dam, would you just multiply that by 100 as well, the same thing you did to the length? And the answer should be, I'm not sure, right? I don't know. Couldn't I? And the answer is no, you shouldn't be able to do that. What we need to do is work through this dimensional analysis. So we use dimensional analysis and something we call similitude to try to relate these scaled relationships. Okay, what is dimensional analysis? Dimensional analysis, it's a formal approach for determining which system properties should be included in a laboratory model We can think of that as a laboratory scaled model and how they can be related. Similitude, on the other hand, is essentially the measurements made in the laboratory that can be used to develop models of a real system based on scaled experimentation design. Maybe I'll just call it experiment design. I don't know that it needs to be experimentation. Oops, this should be a DE. Okay. So the way that we do this is with the Buckingham Pi theorem. Okay, so I'm going to launch into that in just a moment. But before I do, I just want to remind you, going back to in your book, table 1.1, the very first table in chapter 1 looked like this. And I cut it in half so I could fit it all on here, but you get the idea. Remember that we have the FLT system and we also have the MLT system, right? So for if we're looking for density, note that density has in force, it's force per length to the fourth times time squared. And really that's because we're trying to get mass out of this, and mass equivalence to force, we have to go through acceleration to do that, right? On the other hand, density is very easy to represent in the mass system, mass per length cubed. Right, so all of these exist. Force exists as just F. Force also exists as ml per t squared. Right, so we're going to use these dimensions when we're working through the Buckingham Pi theorem. All right. So what is the Buckingham Pi theorem? How does it help? It's basically a fairly straightforward system for trying to figure out how to create dimensionless numbers. And so I'm going to go through that today and give you an example of how we work through it. And ultimately, it should help guide sort of how we put things together. So the Buckingham Pi theorem tells us how many dimensionless products are required to replace the original list of variables. So remember a couple of slides ago, we were looking at delta p sub L, and we came up with, 4 variables that it would be dependent on. The fifth variable was the delta P itself, the change in pressure. So what do we do with those variables? How do we somehow distill them into ratios or dimensionless numbers that matter? So the definition of the Buckingham Pi theorem, if an equation involving k variables, so in our case, k was 5 a moment ago, the thing we cared about, and then 4 other variables that should be related to it. If an equation involving k variables is dimensionally homogeneous, remember that term? Dimensionally homogeneous means that essentially that we can put them together and know that they balance out to get non-dimensionality. If it can be reduced to a relationship among independent dimensionless products, where R is the minimum number of reference dimensions. So now K was the number of variables. R is the number of reference dimensions. Required to describe the variable. So remember, dimensions are F, L, T, etc., or MLT. Right, and that would yield something like, did I miss it? Oh, whoops, sorry, I forgot to add something here. K minus R. So if an equation involving k variables is dimensionally homogeneous, it can be reduced to a relationship among k minus R independent dimensionless products, where R is the minimum number of reference dimensions. Okay, so in general, R is going to be 3. It might be less than 3. It probably won't be more than 3 for the work you're going to do. So this is the minimum number of reference dimensions required to describe the variable. So this is FL and T, and essentially then R is equal to 3 here. All right. So in other words, in this case, K, or let's say 4 delta P sub L, we had 5, K equals 5, and R, we had pressure, which is force per length squared. We had D for the diameter, which is a length. And then we also had velocity, which was length per time, right? So we had all 3 of these reference dimensions. So R was equal to 3, whether we worked in mass or mass length time or force length time, we would have all three of those represented. So K minus R would be equal to 2. Okay, so we'll come back to that in just a second. We'll actually define that more formally on another slide. The first slide I want to show you, though, is that Buckingham was real. Like he was a guy, and I can't remember. Oh, Edgar was his first name. I was going to call him Ernie. So he wrote this paper in 1914 to define this process. So the title of his paper was On Physically Similar Systems, Illustrations of the Use of Dimensional Equations. I'm sure this was not a lot of fun to read, but we won't read that. I'm not assigning that to you, and it's probably wonderful sleep aid if you needed it. But for now, let's keep talking about Buckingham Pi and how it works. Let's distill this to the way in which your book provides sort of guidance, and will keep us from having to read a paper from 1914. So it is termed the Buckingham Pi theorem because Edgar Buckingham, used the capital Pi symbol to represent the dimensionless groups. Okay, and the best way to try to understand this or to learn it is essentially to just walk through trying to put it to use in application in a stepwise procedure. So that's what we're going to do now. We're going to walk through the steps and show you how to use it, and we'll do an overview, and then we'll get into the nitty gritty with a very specific example. On the right-hand side, what you can see here is a weir. Well, actually, this is a transition in a channel where you're going. This is like an outflow here. So the flow is going in that direction. You've got a pool on the right-hand side and a channel on the left. How do you create that so that you, for example, try to minimize your velocity here so that you don't scour out all the material in the downstream end? Something like that would be a reasonable objective here. Okay, so what does the process look like? First, if we are given that a parameter that we are trying to predict is some function, so equals f of some other parameters, u2, u3, all the way to uk, where the left-hand side, the left and right-hand side have the same dimensions. So in other words, whatever dimensions are included in u1 are somehow represented in all the other parameters that are included on the right-hand side, u2, 3, 4, etc. We can arrange the equation into a set of dimensionless products called pi terms. And this would look like this. Pi1 is equal to, instead of f, we'll use lowercase phi. We'll say pi1 is equal to phi, some function of that has included, it's a function of pi2, pi3, all the way out to pi k minus r. All right, so k is the number of parameters. R, remember, is the number of our dimensions, reference dimensions. So there are fewer variables. All right, so in other words, in the example we looked at earlier, we had 5 parameters. 5 minus 3 gives us 2, meaning that we now have a reduced set of variables to work with, and we can group things together. So the functional form of this phi sort of equation must be determined using experiments. Okay, so we don't know exactly how they're going to relate. All we know is what we're going to do from the Buckingham Pi theorem is come up with the pi values, pi1, pi2, pi3, etc. And what that's going to allow us to do then is create experiments that say, okay, with these dimensionless numbers, this is what I need to predict, and I'm going to relate that to the thing that I'm going after, that I'm trying to predict. All right, so we perform this transformation by using what we call the method of repeating variables. If you can hear that little dog, it turns out he is the smallest one, and so he is the loudest one. okay, to systematically look for pi terms is what we're doing here.
Professor, what
Yes.
does that say? It says the functional form of phi. What?
Oh, phi of whatever. It just means phi of two parentheses. Yeah.
Gotcha. Thanks.
Yeah, sorry, that didn't come out very curved. Okay, so let's go through this in an example, because this is going to be the easiest way for us to talk through it and learn how to do it. All right, so we can continue our analysis of this pressure drop per length of pipe along a long, smooth-walled, horizontal circular pipe. So first of all, let's list all of the independent variables for this problem. And what we had said was that delta PL is going to be some function of, we said D, the diameter of the pipe, the density, the inertia we need to kind of keep this fluid moving. So rho would be included. Mu would be included because that's a property that tells us something about the resistance to movement. And then V, the velocity, right? But it turns out that this is 1, 2, 3, 4, 5 total variables. Okay, the one that we care about plus the other 4 that we think are somehow going to be involved in predicting what delta P sub L should be related to. All right. Okay, so there are 5 of those. The other, we'll get to the repeating variable part here in a second. I guess it'd be premature to talk about that. All right, step 2. Let's express all variables in terms of their basic dimensions. Okay, so for all the variables we wrote on the previous slide, let's rewrite them and say that they are equal to whatever their dimensionless groupings are. So I guess, in fact, let's just note there were 5 of them, right? So we had delta PL, for example, is equal to, it's going to be force per length squared, right? Like pounds per square inch, pounds per square foot. And then we're going to divide by, because it's going to be over some length, we divide by L. So what that really boils down to is FL to the minus 3, right? And that's how we're going to group that one. So the force is included on the left-hand side with length. We don't have time included yet, but you can imagine it's going to be coming with some of the other terms that we have here. D, the diameter of the pipe, of course, is in dimensions of length, right? Rho, we said, was another one. That's density. If we go back to table 1.1, I called out density there because it's a little bit funny in force units, and I've committed to FLT instead of MLT, but you could do the same with MLT. In this case, in the FLT system, rho is L to the minus 4 T squared, okay? The dimensions of mu, we said the dynamic viscosity of our fluid that's flowing is, if we go back to table 1, it is F L to the minus 2 times T. And velocity, finally, is in dimensions of length per time, right? L T to the minus 1. Okay? And just to reinforce this, you could have used MLT. I just happened to use FL&T, but that last part is really important. Don't mix them. If you mix them, you'll really be in trouble, right? Just because somewhere along the way, you're going to have like a mass divided by a force, and that's not going to help you at all. So start with one of the 2 systems and stick with it. That's key. Okay, what is step 3? Step 3, we're going to determine the number of pi terms, okay? So we note that, we go back to this, we have FL and T just in mu, we have L and T and V in the velocity, we have FL and T all represented in rho, we have length represented in the diameter, and then the delta P, the change in pressure as we move down the length of the pipe, is F and L are represented, right? So FL and T are completely represented across these 5 parameters. So all 3 basic dimensions and in this case it's F, L, and T, but of course you could have done M, L, and T as well, are required to define all of our variables. So what that means is R is equal to 3. R that we defined several slides ago, the number of these basic dimensions or reference dimensions that are required is 3. All right. And there, as we said before, are 5 variables total. So that means that K is equal to 5. Okay? Now, the number of pi terms, as it turns out, this is a capital Pi, is equal to K minus R, which is equal to 5 minus 3, which of course is the math we can do without our expensive phones or computers. We get 2, right? So what this means then is that the relationship that we're going to look for is pi 1 is equal to phi pi 2. Okay, so pi 1 and pi 2 are 2 dimensionless groupings, meaning we're going to use those parameters we wrote on the previous slide. And the rest of this process is to show you how that works. But we're going to somehow combine them in ways that give us 2 dimensionless numbers, and we're going to relate them to each other. Now, what we would do, what all this sets up for us is whatever pi 1 comes out to be, some ratio or product of some of these factors or these parameters, we're going to go into a modeled system and we're going to measure the things that would give us that product. And that's going to be equal to some function of this other dimensionless quantity, pi 2, right? But it might be 5 times it. It might be 1 over it. Like, we don't know what phi exactly represents, but phi is just some function, right? It just says, well, pi 1 is going to equal, 2 times pi 2, whatever. We don't know that until we do the experimental work. But we have to set this up before we can do the experimental work to inform these, figure out how they're related to each other. Step 4, now we're going to select repeating variables from the list of possibilities. So we had the one that can't be included is the one on the left-hand side, the thing that we're looking for. Okay, so the list of possible repeating variables are the 4 that we wrote on the right-hand side of that original equation. Delta PL is equal to some F function of d rho mu v, right? Diameter, density, viscosity, and velocity. All right. So what are we going to do? We've got those 4 opportunities. Which ones matter? So the repeating variables will be used to form each pi term. Okay. So previously I just said, when we talked about it over here, I was like, yeah, we're going to right here. Sorry. We're going to group some of these things together to make a pi 1 and a pi 2 term. Now what we're told is the repeating variables, some number of some set of d, rho, mu, and v, 1 of them, 2 of them, 3 of them, 4 of them, something, will be used to make each pi term. Well, that's helpful, gonna help us out a little. They must be dimensionally independent, so you cannot form a dimensionless product. They must have the same number of repeating variables as the number of reference dimensions. And there were 3, let's just say R equals 3. So the number of repeating variables also has to equal 3. Okay, so that's helpful. So it is going to be 3 of these 4. We cannot choose an independent variable to repeat. In other words, in our case, delta p sub L, as I mentioned earlier, is off the table. That can't be one of these repeating. And we want the simplest variables to repeat. And we'll talk about why in a little bit. Let's see. This is my next one. All right. I'm going to continue step 4 on the next slide. There wasn't much too much to write there. So in this example, we can select V, D, and rho to represent the simple fluid system properties. So what have we left out? We left out mu. Is mu more complicated than the rest? Hard to say. I mean, rho has F, L, and T all included, but these are pretty simple to deal with. All right, so V and D in particular, compared to rho and mu, are the simplest. In this case, we've chosen mu as rho as a fundamental simple variable over mu. Also, no combination of, in this case, D, the pipe diameter, and V, the velocity, will eliminate density's force dimension, right? So that means that these are dimensionally independent, and that was key. That was something we said on the previous slide. One of the bullets was they had to be dimensionally independent. So remember, V is in length per time, D is just in length, dimensions of length, and rho is dimensions, force, length to the -4, T to the -2. Did I put that minus in by accident? I think I did. No, I'm not sure if that one was wrong. All right, I think I've got a problem with, well, I hate to go all the way back. I'm going to make you guys sick if I go all the way back to that table 1.1. I have a feeling that I think this minus is actually not warranted. I think it's just squared, times squared. Okay. I do have it in my notes for some reason, but I have it both ways, so so I don't know which one is right. Okay. So step 5, we need to form our independent pi terms. Okay, so how does this work? Pi 1 is equal to, now what we're going to do is take delta PL, the thing that we're looking for, right? The thing we're looking for on the left-hand side of the original equation we wrote, and we're going to multiply it by D to the A power, V to the B power, rho to the C power, and our goal is to get all of the dimensions to work out across these terms to end up being F to the 0, L to the 0, T to the 0. So what that means is I'm going to rewrite each one of these variables in terms of their dimensions and figure out A, B, and C so that I get unique values so that F, L, and T all end up with 0. Okay, so let me show you how I do that. So to be dimensionless, to be or not to be dimensionless, pi 1 can be rewritten now in terms of the dimensions for each of the variables. So pi 1 is equal to, what did we say that delta p sub L was? We said it was F, L to the -3. Right? We raise that to the A power, and then the diameter D is just length, the dimension of length. So we raise that. Oh, I'm sorry. The A doesn't go there. The A goes on D there. Sorry about that. So the A is only applied to the diameter, and it's got dimensions of length. Then we have the dimensions of velocity, so length times the -1, and we raise that to the b power, and then we multiply by our dimensions of density here, f, L to the -4, T squared. And we multiply that by, or raise that all, pardon me, to the C power. And this is going to have to equal F to the 0, L to the 0, T to the 0. So what we're doing is essentially algebra up in all of these powers, right? So what does that look like? So what we do now is break this down by each dimension. So for F, you can see that we have F here. So there's one F coming from there. There's no F's to the A power. There's no F's to the B power. There is an F to the C power. So 1 plus C equals F to the 0, 0. Okay? Now what that means, of course, is that C is equal to -1. All right? So ultimately what we're trying to do is figure out what A, B, and C are going to be. For length, now we have a -3, that's a constant. And then we have length, so we have the plus A, we have plus B, and then we have length to the -4, so -4C. And all of that, of course, equals 0. Now, part of the problem here is for length, we only know C, we don't know A or B yet. So we can't quite solve this equation just yet. But not to worry, to the rescue comes T, time. And now there's no inclusion here from the dimensions in our delta P, P sub L. So there's also no dimensions in A. We have a minus B, and then we have 2 plus 2C is equal to 0. Okay, so now, because we know C is -1, we can determine that B is equal to a -2, right? And then when we put these together, we end up with A being equal to 1, okay? So in other words, all I did was I took my -2, plugged it into here, took my -1, plugged it into here, and when I solve for A, I get a +1, okay? So now let's take this back and put our pi terms into place, all right? So what this looks like then is pi 1, we go back to this master equation at the top, is equal to delta PL times D, right? D is basically D to the A, so D to the 1 power is just D. Then we multiply by V to the B power. B is a -2, so we have V to the -2, and then we multiply by rho here to the C power. C is a -1, so rho to the -1. Okay, now we could rearrange that such that essentially pi 1 is equal to delta PL times D divided by rho V squared. Okay, so that's our first dimensionless grouping. Realize we're running low on time. I just have 2 more steps, and then we'll get to I think I can get through them pretty quick. So that's our first dimensionless grouping. The second dimensionless grouping looks like this. So what did we leave out? We have delta P included here, but of the 5 factors or 5 variables that we identified earlier, we now have to go to the other one that is not repeating. So D, V, and rho are going to show up again, but instead of delta PL, we're going to now have our mu. So pi 2 is equal to mu times the diameter raised to A, velocity raised to B, and rho raised to the C power. When we go through this process again, we write this out. Remember, mu is in dimensions of force, length per length squared times time. The diameter of the pipe is in dimensions of length. We raise that to the a power. Velocity is length per time, raised to the b power. And rho is f L to the minus 4 t raised to the c power. And all of this is going to come out to be f to the 0, L to the 0, t to the 0 power. So for F, force, we end up with 1, right? No A, no B, 1 plus C is equal to 0. And that means that C again is equal to a minus 1. So that's useful. For length, oh, goodness sakes. For length, we end up with what? A minus 2 here. And so we're just working with all of our exponents. Minus 2, we have plus A, we have a plus B, and then we have a minus 4C is equal to 0. Again, we don't have enough information to solve that, so we don't know what A and B are just yet. Now if we go to T, for T, we end up with, we get 1 time in mu. We have nothing in A. In the B group here, we have a minus B, and then we have a plus C, and we know that has to equal 0. And again, because C is a minus 1, we can solve for B also being equal to a minus 1. And then together, these tell us that A also works out to be a minus 1. So the linear systems here, we have 3 equations and 3 unknowns. So that means that pi 2 is equal to mu raised to, well, by itself, it's to the 1 power. D is to, everything else goes in the denominator. D, V, and rho. Okay, so that's essentially how that comes out. Now we just put these together on the next slide. The very last thing here is just putting pi 1 is equal to phi pi 2, and all I'm going to do is replace these terms. Alexi, did a question come up?
Yeah, I was pointing out, should the rho have a t squared? And then I think that might miss. And then maybe that's why B looks like it should be 0 the way you've written it, but maybe because of that it should be negative 1.
Let's see, my rho. Yep, I forgot the 2 there. Thank you. This 2 right here, which makes this. That was T, so T is
2C.
plus a 2C, right?
Yeah.
Sorry about that. Okay. Wow, I have a systematic problem in my notes here, but okay, thanks for that. So that now works out to the minus 1, minus 1, minus 1, right? So 1 minus 1 plus 1 equals 2, making C minus 1. Yep, that should work out to 0. Okay, so the last thing, let's just put these together. We said pi 1 is equal to phi pi 2. And what this looks like then is delta P sub L times D, our pi 1 term, so divided by rho times V squared, is equal to phi, some function of this dimensionless number, mu over dv rho, dv rho. Okay, since we used FL and T, you could use ML and T to check that pi terms are dimensionless and get the same thing. All right, so we're right at time. The next thing I have, I'll just give you a second to write this down. The next thing I have is just our participation. So if you can hang out for just 1 minute, I'll give you 10 more seconds to write that down and get caught up. All right. A 1/20th scale model of an airplane is used to determine forces on the actual airplane. The 1/20th scale refers to what? Lengths, velocity, forces, or Reynolds number, or none of the above. So go ahead and get your responses in. If you are going to go buy a model that is 1/20th scale, what does that refer to? You can go to hobby shops, Michaels, whatever, buy these. They might be old World War II airplanes or something like that. When they say that they are 1/20th scale, what does that mean? Is it because of length, because of velocity, forces, Reynolds number, or all of the above? We haven't even talked about Reynolds number. We've got 84 folks online, so hopefully we'll get at least 84 responses. We'll cap it at 60 seconds here. I know some of you have had some troubles with getting Reef or your iClicker to work. If it's not working for you, before I end this, send me an email with like a screen capture that like here's what's happened, but you didn't vote, and at least I can get that included in the scoring for today, participation points. Okay, we're at 82. I'll go up to 110 here, 9, 10. Okay, what do we see? All right. The majority of the class said that this is due to lengths. The second most was none of the above, or pardon me, it was all the above, no, none of the above. It turns out it is A in this case, that just when you ask for 1/20th scale, and generally that's about lengths, the total size of a thing, that doesn't necessarily mean that you'll have 1/20th the velocity, right? So that's an important aspect here, is just simply knowing that length scales will not translate to functional scales, and that's why we go through this entire process. All right. Great to see you all again. Have a good weekend, and I look forward to seeing you at recitation on Monday afternoon. On Sunday evening, I will have posted the 4 problems or so that we'll go over. It might be less given how long these are, but I'll post whatever we're going to go over in recitation on Monday. So see you all on Monday. Take care.
Do you mind clarifying quick why we left the viscosity out of the original equation solving for pi?
Yeah, so we could have used it instead of rho. In this case, I made a decision that rho was just more of, what did we say there? The simplest of the variables. So when we had diameter, velocity, density, and viscosity, we didn't want to include both viscosity and density. So we needed to choose one of those two because those were the two most complicated ones when it came to the dimensions that were included. So we chose that one. We probably could have done it the other way and come up with different pile groupings that would still be valid. Does that make sense?
Why wouldn't we want to include both?
Because the rule was that you want to include the simplest of the variables, and because both of them had F, L, and T all represented. That meant that and the others only had 2 of the 3 or 1. We needed to include the 2 simpler ones to begin with, and then make a choice between those 2 about which one would be simpler.
Okay.
Does that help?
Yeah.
Great. You bet.
Basically, we're trying to avoid making those equations really complicated, because if they're really complicated, we can't solve them, and then we're not going to be able to do it. So
yeah.
And that's because your R was equal to 3. That we used 3. So.
Yeah, the 3 reference dimensions are. Yeah, in general, that's going to be 3. It might be 2 or 1, but it shouldn't be greater than 3.
Okay.
The problems you're working on.
I had a quick question about the homework that was due today. I can share my screen quick.
Okay.
Oh, it's not letting me. Oh, wait, there we go.
There you go.
So this was one that I got wrong, and this is the answer. And the reason I got it wrong was because for velocity, I did 110.5, which is like the answer if you like use all of the significant figures.
Okay.
And if you plug it in, you will get like my answer, which was, I think.
Real quick, this is number 3. Oh, this is the one with the veins. Okay.
Yeah.
Yep.
So yeah, I re-plugged it into like the solution, my velocity, and I got 15.6. So I was just wondering, I just figured I'd ask about it just because I spent like 4 hours on it.
Jeez, holy cow. Well, Emma, send me, so a couple of people have sent me, we did find one error. I don't think it was on this problem though. I'd have to go back and look. A couple of people have sent me problems with basically math errors that it looks like are built into the Wiley Plus solutions. So can you give me a screenshot and then tell me what you put in? I know I'm asking you to retell me what you just told me, but I can then kind of spend a little more time looking at this and figure out where that error was and try to get you your points back. Does that work?
Yep.
The one other thing that I want to tell you is we what we'll probably end up doing is if we add any credit back, we need to do it on part 2 or 3. Somebody told me today I added a point back to their Wiley Plus piece, and then it got changed back to the original. So there is some updating that's going on between Wiley Plus and Canvas, and it's undoing any change we make to the grades. So remember, because we're adding everything up, it doesn't matter. But if you get over 1 for part 2 or 3, that's because it's the credit coming from part 1. Does that make sense?
Yeah, that makes sense. Okay, that sounds good.
Great.
All right, thank you.
I can't promise it by tonight, but probably over the weekend.
Okay, no problem. Thank you.
Thank you.
Do you have time